Hello, good evening once again. Welcome back. And gradually, we are closing in to the end. Hopefully, we should be able to finish by tomorrow. If you're unable to finish by tomorrow, I will indulge under the probably the Sunday or Monday, whatever, to make up. But we necessarily have to finish. And so we are going to start. So as of yesterday, I think you dealt with because we have done enough. Just a minute, please. Thank you. I'm back. So yesterday we tried to look at the morphology and what you ought to do. We've extensively tackled the issue of viability and the fact that it isn't anything that is so um, difficult for anybody to want to do, and that, of course, it is not a regular part of semen analysis unless there is an indication for it. And indication is that your immotility fraction should be more than 60%. So that if you have just about less than 40% of sperm showing total activity, and talking about total activity, you're talking about any movement of a kind. If that total motility is less than 40%, then there's a cause to find out whether the immotile ones are alive or indeed dead. That's where you come in with the eosine test. And we talked extensively about the viability eosine test. And therefore, we said that the principle could be twofold. Either the dye exclusivity, that because the sperms are alive, then they will exclude entry of macromolecules such as the eosine. And that is the dye exclusion. We're also talking about the membrane integrity, where you're saying that because the membrane is still intact and therefore not amenable to just any inclusion, then they will also resist any entry of dyes such as the eosine. So I think whichever way you want to look at it, then it means that the live sperms will remain unstained, very, very unstained, clear. And then those that will stain pinkish are those that have picked out the eosine. For that matter, they are dead. And you're saying that, so dead will stain red, okay? Right. So another element we're going to look at is round cells in semen, what we call round cells. All right, so we move on. So the ejaculate usually contains cells other than spermatozoa. So you expect that the ejaculate, that the seminal fluid, will be made up of the seminal plasma and the sperms. But as we move along, you see that there could be cells other than the spermatozoa. If for nothing at all, you appreciate the fact that if semen is collected via the coitus interruptus, then it is likely to be contaminated by epithelial cells from the vagina. It's likely to be contaminated by, let's say, even bacteria from the vagina. It's likely to be contaminated by red cells from the vagina if the probably the woman is actually peri-menstrual, I mean, around the menstrual area period, and then probably he just want to help the man to collect the specimen. He allows the sexual activity to take place. Then, of course, you expect that there's going to be some remnants of red cells, and all these are going to be found in the semen. So you should be able to identify cells other than spermatozoa, and you should be able to also understand the significance of it. Are they significant? Are they important? Should you report? Should you not report? And all of that. So this is what you're going to do. And why are they called round cells? Let me quickly go to the next slide and you appreciate. Round cells in semen may include epithelial cells of the bladder. Remember that the semen is coming from all the other ducts through the prostate and then from the urethra and so forth. Of course, sometimes, the bladder neck. So you could have some cells from the bladder. All of them can be found in the seminal fluid. And they are collectively referred to as round cells because they all appear round under the microscope. So under the microscope, whether they are epithelial cells, whether they are immature sperm cells, whether they are white cells, you see that technically they'll be round. And therefore, you may have to do an extra work to be able to know that, oh, this is indeed an epithelial cell. This is indeed a white cell. This is indeed an immature. Otherwise, on the face of the microscope, I'm talking about the unstained wet mount. There's no way you're going to see them as either white cells or immature cells or what have you. So to avoid any kind of misdiagnosis, they are called round cells. So it's like when you have white cells, you can say they are white cells. Then you may have to do a test to know that, oh, this proportion is neutrophils, this proportion is eosinophils, this proportion. Otherwise, if you do an ordinary white cell count, at that point, there will no way you'll be able to differentiate between the neutrophils and from the eosinophils. So collectively, you say you are doing white cells, unless you do, let's say, a film comment or a differential count, where now you're going to be able to differentiate between the neutrophils and so forth and so on. So what we're saying here is that on the face value, most of the cells you see, other than the sperm cells, they all look round. Okay, so if you say round cells, you are not competing yourself. You don't want to say, oh, this epithelial cells, only find out, oh, it's not even epithelial cell, but it will be immature sperm cells. All right, so once we say round cells, anything which is round, and they include the epithelial cells from the bladder, epithelial cells from the prostate, epithelial cells from the urethra, they all look round. All right, that's why collectively they are called round cells. So by conventional light microscope, it is not possible to reliably differentiate between the polymorphs. The PMN is the polymorphonuclear leukocytes. And technically, these are the neutrophils. And multinucleated spermatids. These spermatids are also the immature sperm cells. On the face value, like in the light microscope, there is no way you can be able to differentiate between the two. All right. So let's go back again. So the cells that can be found in the semen will include white blood cells, which you may want to call it past cells. You also call it leukocytes, so whichever way. And they are predominantly polymorphs. You can also only say polymorphs or polymorphonuclear leukocytes or polymorphonuclear neutrophils, whichever way. We just want to be, so scientific that whichever way anybody describes, you know what it is. And you know that certain terminologies can be used interchangeably. So white cells or past cells, leukocytes, and all of that, you know that they are about the same semantics, and you know when and how to use them. All right. And of course, red blood cells, and then spermatogenic cells, they are immature sperm cells. Technically, you don't expect the immature sperm cells to be found in the ejaculate, but occasionally you can have some. But at what point is it becoming problematic? So these are things that we're going to look at. There can also be other cells in the ejaculate. These are the polygonal epithelial cells from the urethral tract. And because they are polygonal, it will look on the face value, to look rounded. Of course, you can also get some trichomonas, you can get bacteria, you can get some debris. And you know that when you have any of this, you should be able to interpret what it means. Right. So now you come back to where you went earlier, the round cells, the fact that they all look round. Now, if you have round cells collectively and you're getting less than 10 per high power field, you can ignore them. Okay, you can ignore them. Whether they are white cells or epithelials or whatever, you can ignore them. All right. Then once they are more than that, then you want to know, because we said that it could be epithelial cells, it could be polymorphs, it could be the immature sperm cells collectively. So if they are more than 10 per field, they want to know which of them is contributing to this high count. All right. But if all of them are less than 10, you can ignore them. I mean, it means that they are still within normal range or acceptable count. But if it's more than 10, they want to know what is contributing to that proportion. All right. So if more than 10 per high power field round cells are found in the semen, a portion of the ejaculate should be specially stained to look for white blood cells. Okay. All right. So to differentiate round cells from the polymorphs, and for that matter, the white cells, examining a stain smear and or a peroxidase staining is useful. Okay, so what it means here is that once the round cells are more than 10, first and foremost, what is going to be a problem or what is going to be most clinically significant will be white cells. So you want to rule out whether it is white cells that is accounting for that high quantity of the round cells. Okay, so your interest would be trying to look out for white blood cells. The rest, if they're even mature cells or some epithelial cells, most of them are clinically insignificant. Okay, so your main interest is to look for the leukocytes. Typically, you'll be looking for the polymorphonuclear leukocytes, and that will be neutrophils, okay? And you know that neutrophils are key indicator for infection. So straight away, that is your interest. You want to look at whether there's an infection in the genital tract. So you are either going to use stain, smear, and in this case, even your GIMSA will do. All right. You can do your GIMSA stain. That will be okay for you. Right. So that you are going to look for, here, the interest is that you're looking for leukocytes. And if you do a GIMSA stain, of course, it will tell you whether you're dealing with neutrophils or some lymphocytes of a sort. And then there's also a test called the peroxidase test, which you will look at it very soon. All right. So these two, if you do even one of them, if you have the resources to do both, that will be perfect. If you don't have the resources to do both and you have what it takes to do just one of them, either of them will help you to identify whether you're dealing the round cells that you're seeing are white cells, and for that matter, polymorphs, or nothing of significance. So in a stain smear, like we're saying, you can either stain or do the peroxidase. And most often, I'm sure that the staining will be the most easily available option. So in a stain smear, differentiation is based on differences in coloration and on nuclear size and shape. Of course, so if you have a stain smear, of course, leukocytes will stain bluish, and the spermatids or immature cells will also stain pinkish. And so straight away, you know that you're dealing with leukocytes or you're dealing with this. And then, of course, the nuclear size and shape. The polymorphs will always have a polymorphonuclear type of nucleus. This one, from our knowledge in hematology, you'll be able to easily discern which one is a neutrophil and which one is not a neutrophil. All right. So then, because we said that once the round cells are more, you want to find out which one of them is a white cell. So you do the staining, which we talked about very, very easily. And then you can also have a peroxidase activity test. Peroxidase activity test is actually a histochemical technique. Right? So those who are in histopathology, I'm sure these are things that you do almost all the time, histochemical techniques. So, and it's based on the fact that you know that neutrophils have granules. So that's why you call them granulocytes. I'm sure you know this one from basic hematology. So the granular size have a prejudice. Okay, so this is the test that you are trying to look for. So once you have and some macrophages too could have granular size, which will test for positive for prejudice. So once you are seeing a positive prejudice test, then you know that you're dealing with some neutrophils. And if they are neutrophils, then it means that it's an indicator for infections. All right. And then if they are lymphocytes, of course, immature stem cells, they are also prejudice negative. So you do your prejudice test. If it's positive, then you are getting what you are suspecting, which is the neutrophils or the polymorphs. If they are negative, then it could be other lymphocytes or immature stem cells, which may not be of great clinical significance. All right. So checking for prejudice positive cells in semen. Now, once you are checking for prejudice positive cells in semen, you are definitely looking for white cells or neutrophils. Okay. So you do the test, but the test will not detect polymorphs which have released their granules. So, for example, if you shake your semen too much, if you shake it vigorously, and in case that specimen has white cells, you are likely to rupture the white cells which are in it. And once they are ruptured, what it means is that the neutrophils are going to be degranulated. I mean, they are going to release their granules. And once they lose their granules, when you do the test is looking for granules which contain the prejudice. Meanwhile, the granules have been degranulated. They have been released already. And so even though the cells are there, the prejudice test will show it as negative. I'm sure this is something that you can easily appreciate. So activated polymorphs, okay, which have released their granules will test for negative. And then, of course, lymphocytes don't have granules. Monocytes don't have the granular size, and therefore, all of them will show negative for the prejudice test. If you look at the right on the picture, you are going to see some pinkish stained round cell there labeled as P. And so this is a prejudice positive. It's likely to be a white cell. The other one on the left, you see that apart from the one being pinkish and the other one almost colorless, you cannot see the difference between the two. So on the face value, the best to do is to report this as round cells. They are round. But when you do the test, you saw that one is positive, one is negative. The one which is positive is a white cell. The one which is negative could be immature sperm cell or even a lymphocyte. Okay, so that is how it is. So if you do your wet mount and you saw a lot of white cells and we are concerned, sorry, you saw a lot of round cells and you were concerned, you will do a test, either abstain or do the prejudice test, and then you saw that they are all the round cells are predominantly white cells. What does it mean? So in that case, then if they are white cells, then the presence of white cells in the semen, you know already, is the leukocytopenia. So leukocytospermia or pyospermia. When you want to call them past cells, they become pyospermia. If you want to call them leukocytes, they become leukocytospermia. All right. So then what next? Then you have to now go and do a cell count, okay, which we'll talk about later. So you do a white cell count manually. And if you are getting more than 1 million per mil, then it is an indicator of infection. Okay. If you are getting more than anything less than 1 million, you consider as normal because you don't expect the semen not to contain any white cell at all. No, there could be some white cells, but if they are not too much, they are not too many, I'm sure they could be considered as normal. So anything less than 1 million per male of white cells is considered as normal in semen. If it's above, then it's suggestive of an infection. In this case, semen culture must be performed in order to confirm the infection. All right. And then the semen analysis should be repeated after treating the infection. So you're seeing that the white cell count becomes significant here. That if there is an infection somewhere, it must be indicated. It will be indicated as leukocytopenia when you have actually confirmed from your initial round cells population that these are actual white cells. So therefore, you have done your cell count, and then they are more than 1 million. So it is presumptively leukocytopenia, and for that matter, infection. But it can be confirmed through a culture where now the causative organism can be isolated with subsequent antimicrobial susceptibility testing. All right. Now, even if at that point your sperm count is low, you don't recommend that the patient should be treated for the low sperm count, because you know that if there's an infection, that infection could also contribute to the low count. Remember, we said that whenever there's infection, the cytokines produce cause an overproduction of the ROS, the reactive oxygen species. And whenever you have an overload of reactive oxygen species, they will normally produce oxidative stress, because the body's antioxidants will have been overwhelmed by the overproduction of the reactive oxygen species. And the negative balance is what is called oxidative stress. And oxidative stress is a danger to life of all cells. Okay. So, and of course, the sperm cells. So sperm production and even everything will go down. So why are you treating the low sperm count when there is all indication that the patient has an infection? It is the infection that's probably causing the low listen. So the best thing is to recommend that the treatment, so the infection be treated. After the infection is treated, you give it some little time to repeat the semen analysis. And then you see that once the infection has cleared, of course, the first indications is that your round cells level will come down significantly and that to become normal. All right. So in that case, then you can now recommend, if there should be attention on sometimes even when the infection is gone, you see that the sperm count will also increase automatically, because your ROS level will have gone down significantly, allowing the body to produce its normal range of sperm cells. All right. So significance of cellular elements other than sperms. We talked about the round cells, if there could be other cells. Of course, some other round cells are the epithelial cells. Some of the other cellular elements that may be found in semen may be clinically irrelevant. For example, the presence of epithelial cells in semen is never associated with any pathology. If you are saying epithelial cells, you cannot associate it with any pathological condition. All right. If for anything at all, especially if the epithelial cells are present with some bacteria also, this could be a strong indication that there was a vaginal contact. Okay, so if many epithelial cells are present in semen and they are covered with bacteria, then it is most likely that the sample was obtained by coitus interruptus and that the cells with bacteria originate from the vagina. I hope that point is very well clear. All right, so when the person has told you, oh, I collected the sample by masturbation, yet you're seeing a lot of epithelial cells with bacteria, please, you can put on your last bet and tell the patient that, master, from what I'm seeing, you touch somebody's vagina. All right, that's just that way. So the presence of RBCs these are also cells other than spermatozoa. It's a manifestation of injury or malignancy of the genital tract or rupture of the blood vessels or infection. In this case, you should rule out what do you call it? Coitus interruptus, because most times, a lot of time, from my experience, a lot of time, some men have a challenge masturbating, and so even as you recommend that they should masturbate, then remember you also said that sometimes when somebody is masturbating and he has a wife with him, that also facilitates, it stimulates. And sometimes the man will do, even the woman will help you. The thing is not happening. So okay, let me fashion kakra. And then you only shame one, then no. Meanwhile, you will come and tell, because that most of the time, you have spent a lot of time trying to masturbate. He thinks that let's say the 30-second insertion he did cannot be regarded as coitus. Okay, and then that is that. So, but once you get some of these things, you must be RBCs. You don't rush and report about RBCs unless you are convinced that no, it is not coitus interruptus. This is masturbated sample and the RBCs. Then there could be some injury somewhere. All right. Yeah, there is what called sperm aggregation. Please take note of sperm aggregation and sperm agglutination. So sperm aggregation is also one of those things that could be clinically insignificant. Okay, so aggregation, when sperms are dead, and so let me read and then you understand. Sperm aggregations can be recorded, but it's usually not clinically significant. The adherence either of immotile spermatozoa to each other or of motile spermatozoa to mucous strands or epithelial cells or debris is considered to be sperm aggregates due to non-specific aggregation. So what it means here is that sometimes you can get some debris somewhere, and then even if there are motile cells, there are motile sperms, they get themselves entrapped within the debris. So you see them as it, that is not an aggregation. So if you have even large sperms entangled with some debris or with some other cells or something, that is not an aggregation. Sorry, that is not an aggregation. That's an aggregation. Or sometimes all the cells will have been dead and they have been also entrapped by some other non-spermatozoa cells. These are all aggregates. You can report them as aggregates, but they are clinically not significant. They don't mean anything. What is clinically significant is what we call sperm agglutination. So attention should be paid to the presence of agglutination of spermatozoa where motile sperms are stuck to one another. Remember we said that when you have motile sperms stuck to, let's say, some debris or some epithelial cells or something else, which is obstruct, especially mucus. Remember we said that if you do a wet mount and there is incomplete liquefaction, you could see mucus strands. You know a strand, I mean, like some, how do you call it? Some kind of a fiber of a sort. And then you see that these are mucus strands. And they could entrap some sperms movement. All right. Those are aggregations. However, if you have those sperms that are supposed to be moving, but one is entangled with the other, which is also, they are all motile, they are stuck to each other. That is an agglutination. So agglutination can affect sperm motility and concentration. Okay, right. So sperm agglutination specifically refers to motile spermatozoa sticking to each other, either head to the head or tail to the tail, or a mix. I mean, either the head to the neck or something. So you see that one spermatozoa is stuck to the other at the head, or stuck to the other at the tail, or stuck. You see that they are all struggling to move. That is, and even if they are small amount, even they are small amount, that is an indication of agglutination, and that is very, very, very significant. Okay. So any motile spermatozoa still on sperm agglutination, any motile spermatozoa that stick to each other by their heads tails or midpits, even if the presence of only a few groups of small numbers of agglutination spermatozoa, they should be recorded as sperm agglutinates. The presence of sperm agglutination alone, however, is not sufficient evidence to deduce an immunological cause of infertility. So we are going to go to one point where when you have sperm agglutinase, then there is potentially anti-sperm antibodies. Okay, but when you see agglutinase alone, you don't conclude and say, oh, then there is some immunological condition that's causing the infertility. You don't do that. So you could suspect. It's like when you had the round cells, you could suspect that, hey, they could be white cells. But you just on the basis of that, you cannot conclude that they are white cells unless you do a test to confirm that they are white cells. Basically, if you are getting that goodness, you can't conclude and say that there's some immunological cause. You have to do a test to confirm that there's anti-sperm antibodies. I hope that point is clear. So sperm agglutination is suggestive of the presence of anti-sperm antibodies. And then testing for anti-sperm antibodies must be considered in such situations. I hope that point is clear. Just as we did with the round cells, you suspect that there could be white cells. So you do a test. If you do a test and indeed are white cells, you can only suspect that there's an infection, but only confirmation is to do a culture. So you do the culture to confirm it. So similarly, you get sperms that are supposed to move, they are unable to move, they have aggregated themselves together. You see that this aggregates is not a matter of some debris which is causing cells sticking to each other and causing them not even to move. That becomes an agglutinate. You could suspect that there is anti-sperm antibodies, but that is your suspicion. Then you have to do a test for anti-sperm antibodies. I hope my point is clear here. So in that case, once that you are suspecting that there could be anti-sperm antibodies, then if you have a facility that does all these tests, you don't go and do it as part of semen analysis. It's like when you do your urine analysis and there's white cell count high, you can only suspect that there's an infection and therefore recommend that there should be a urine culture. But that doesn't mean that there and then do a urine culture. Okay. There is, however, let me now divert with that. However, what you call reflex testing. Reflex testing is not any elsewhere. What it means is that if a physician requests for, let's say, sickling, and then he reflects, then what it means is that if the sickling is positive, don't send your sickling report to a doctor only for the doctor to come back and say that do electrophoresis for me. Okay, so in the reflex effect, he's saying that go ahead and do any subsequent test which you deem will make diagnosis complete. So if you have, let's say, there's a reflex for film comment, what it means is that, oh, if you do your HB and it's below, let's say, a certain value, if any HB below, let's say, 7, do film comment. So it means that you are not going to take the report to a doctor only for the doctor to now come and back and say that do a film comment for me. So those are the things we call reflex testing. Reflex testing is once you set a certain basis and the basis request for a further check. What makes reflex testing workable outside is that they charge the patient based on the number of tests that they are doing. And most of the charges too are borne by insurance. So if they did the test and then they reflex to do another test, they will charge accordingly. But here the patient comes in, he pays for what the doctor has requested. So if he comes to do, let's say, urine RE, and then from the RE, I think that you should do culture. I don't give the report to the doctor. I have to, by reflex. In that case, the doctor too will have indicated a reflex. So once I indicate a reflex, it means that I have the right to do any subsequent test and charge the patient accordingly. But here the patient has come and then pay for the urine RE and it's gone. If I go to do any reflex and go and do a culture, who pays for the culture? And even if the patient doesn't come back for the, it means that it's so. Those are some of the things that you're talking about. So, for example, I've said that elsewhere where there is this reflex mechanism, what it means is that if you do test A and it gives an indication for a test B, go ahead and do that. So reflex testing is not a particular test. So I say, when I say reflex, what type of test is called reflex? No. How that somebody is getting it right. Okay. So like we're talking about the round cells. If you do semen and round cells are higher, go ahead and do, let's say, your peroxidase test. That one, the patient will be charged because it's not part, the peroxidase test is not part of semen analysis, the routine semen analysis. So you do your peroxidase test and it's also high, then it means that you confirm that it's infection. Go ahead and do your semen culture. And all those things is reflexing, and the patient will be charged accordingly. All right. But here, if you do that, your lab will run down because the patient doesn't know that you are doing anything additional. And when it comes, he won't pay. All right. So that's just by the way, I think you have understood me. So for the sperm agglutination, not the aggregation, you suspect that there are anti-sperm antibodies. Then if resources are available, you go and do the anti-sperm antibody tests. And there are two methods that are well recognized. One is called mixed agglutination reaction assay. The mixed agglutination reaction becomes MAR, the MAR test. So the MAR test, it tests for only IgGs. Okay, tests for only IgGs. You know what IgGs are? IgGs are for chronic conditions. And then you have the immunobead binding assay. That will check for IgG, IgA, IgG, and IgMs. Okay, all right. So this is just for mention. If there is time for us to talk about these things, we may talk briefly about them. But for now, just to know that there could be an indication for anti-sperm antibodies when you're seeing sperm agglutinase. And the tests that are available are the MAR tests and then the immunobead tests. All right. So we said that if even there are small agglutinase, they are important. So what do you mean by small? So that's the evaluation of sperm agglutination. So the sperm agglutination can be graded as follows. So we have grade 1, where there are only few. So you can either, if you are, the doctors may not be comfortable or they may not understand what the grade 1, grade 2. So grade 1 would mean few. So you can on your let's say rough sheet, you can say grade 1, but you know that grade 1 is few. So in your final report, you say few agglutinase. Okay, few agglutinase. So in the few means that less than 10 sperm per agglutinase. So there are clumps. You are seeing them aggregating, but you see them 3 or 4 or 5 sperms aggregating at a point, at a time. That, so you can only say there are few. All right, so we'll talk about, you see, there are a lot of things that may not be available on the market because the suppliers, somebody's asking whether you have the immunobead available on the market. You see, the suppliers are looking out for their money. And so they are only interested in fast-moving items. So if, for example, only one laboratory wants to be doing the anti-sperm antibody test, unless you specifically direct a particular supplier to get you that kind of kits, You never get it because you wouldn't go and bring a kit only for the kid to come and expire on him or her. All right. So if that's some of the things that if you think you want to do it, probably for research, then of course if it's for research, then you have to find means of getting the case at all costs. But for suppliers to be supplying, they must be sure that they have the market available. And like I'm saying, how many laboratories will be doing this kind of thing? If that's the case, it's like I don't know whether no, it's not your class, but we talked about uh, syphilis, and then we talked about the fact that people are using the RDTs, and the RDTs are actually specific for the trichomes, and they are not VDRL. If you want the VDRL, these days you don't have VDRL kits, but you have the what do you call it? Rapid plasma reagent, rapid plasma RPRs, rapid plasma reagent. But the suppliers are still okay. So is this class? Thank you very much. The RPR, very good. So the suppliers will not bring the RPR because all people are requesting is the kit, and even though the suppliers um, uh, people will write VDRL, the suppliers will only bring in the kit. And that's what is moving on the market. So if you want somebody to bring you the RPR, it must be intentional. And then the supplier also must be sure that when it brings it, you are going to buy it. Okay, so it is a problem for us because we are not driving the market. It's the market that's actually driving us, so to speak. So that's just bad. So if somebody wants to start the extra tests, wanting to do for, firstly, probably you may have to invest in that one and do semen analysis as a project of a sort and look out for sperms, cases that contain sperm agglutinates. When the sperm contains sperm agglutinates, then your first suspicion is that they could have anti-sperm antibodies. Then for all those cases, you do your immunobid. And then then you publish it. That a number of the cases of the infertility, blah, 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 are due to anti-sperm antibodies. And therefore, your recommendation is that apart from the routine semen analysis, people should be interested in also doing the anti-sperm antibody tests. And then you see that now you'll be driving the market. Then people are now doing before you say that everybody is doing anti-sperm antibody tests, and then there's a market for it. The people will now bring in. Otherwise, the situation as it is, I'm afraid the supplier or the market will not be available for some of these things. I hope I've made my point. So when there are only few sperms, then less than 10 per clump, it is called few. So you can say few agglutinates. Remember, we said that even the few, just write it. That's agglutinate because it is a first signal that there could be anti-sperm antibodies. All right. Then, if they're between 10 to 50 per agglutinate or per clump, then that is moderate. If they're more than 50 per agglutinate, that's large agglutinates. If almost all the sperms have agglutinate have become one clump, then that's gross. Gross. All right. So these are some of the sperm agglutinates. And you see that you can have some few, excuse me, let me try to see. You can see some here we can describe as few here. You can describe this one as moderate. You can see here this gross and stuff like that. All right. Right. Can you give me some, can we take a break for 5 minutes? Somebody is just came to me and I asked the person to wait. But for the way things have been, I will seek your indulgence to attend to him for between 5 to 10 minutes. I'll be back. I'm sorry. I'll be back. Thank you for that. Indeed, I'm very, very sorry. I think I've overstayed the time that I requested. Somebody's asking whether the class is over. I get the impression that the person also joined very lately because I've asked permission for 5 to 10 minutes. And so if anything at all, you shouldn't ask whether the class is over. If you ask that, it means that you two were not in class by the time I asked this permission. All right. So let's move on. We're going to do sperm count. So we've done the sperm, a lot of the microscopy work. We finished with the microscopy. Microscopy, we're done with motility, morphology, and aggregation, and agglutination, and so forth and so on. We've done all that we have to do. Then another important point is the sperm count. I'm going to try to introduce to you something unique, something new with the sperm count. So take note, right? So the normal sperm count, also called sperm concentration or sperm density, is expressed as the number of spermatozoa in millions per male of the seminal fluid. The sperm count or sperm concentration or sperm density is expressed as number of sperms in millions per milliliter. That is the way to report it. And of course, the reference now is greater or equal to 15 million per male. Remember, we said that we are used to the 20 million. The current reference point from WHO is greater or equal to 15 million. And I was trying to explain at that time is that what I was explaining at the time is that if somebody was, let's say, had 16 million, all the time he's been getting between 15 to 16 or 17 million per. Anytime you do the semen analysis, it's around that range. At that point, you may classify that patient as, let's say, moderate oligospermia. You would think that the patient is oligospermic. Okay. Oh, yeah. Now, the patient has been on medication or whatever. They're still not been able to father a child or to fertilize. So it means it's still in the range of infertility. Is that right? Because infertility is defined as inability to cause natural fertilization or conception or pregnancy within the period. So it is still, what do you call it? Infertility. Now we are saying that 15 million is normal. So it means that all along the patient 16, 17 is still normal. Is that not it? Yes, it's normal per the new edition. It means that this patient should be reclassified. What it means is that once he was being considered as oligospermia, now it's not oligos, it's normal, but it's still not getting the pregnancy. So it can be reclassified as unexplained infertility. That was what I was trying to say at that time. So that, okay, so what about people who have always been around 17, 18, and we say that they're oligospermia? Now, per the new formula or new reference, they are not oligospermic, they are normal. So if they are normal and still not getting pregnancy, then they can be reclassified as unexplained infertility. Take note on that. All right. So sperm count is perhaps the most widely utilized semen parameter. When somebody requests for semen analysis, the only thing they are looking at is what is the sperm count. They don't look for anything that you write. I'm not sure they even read. Okay. So that is why I say it is the most popular, widely used parameter. Now, but now I'm sure that from what we've discussed, you know that a lot of information can be obtained from the other parameters. Okay. So in the sperm counting, it's usually manual. There's a manual sperm count. Sperm counts are traditionally performed by manual methods using the hemocytometer, that's the counting chamber. Okay, the hemocytometer or the counting chamber. That is what people will normally use. Now, and of course, all of us know about our usual counting chamber, which is the improved neighbor counting chamber. And that's what a lot of us use in our labs. Now, let's see, there is a special counting chamber that is indeed specifically designed to do sperm count. And this is where I'm saying that we're going to get something. Some of you probably, I don't know, some of you may have used it before, or may have seen one before, or maybe. Is there any one of us who knows about the macular counting chamber? Anyone, show by hand, or you can give this impression? Yeah. Anybody who has seen a macular counting chamber before? Anybody? I just can show by hand. If any one of us have seen or known, oh yes. So Andy. All right. So Andy has seen a macular counting chamber before, or even probably have even used it. Okay. So yes, Bright too, seen a macular chamber before. Yes. Who else? Who else? I just want to know so that it becomes easier for me. So 2 out of the lot seen a macular counting chamber. Macular counting. Yes. Anyone else? Andy and Bright have seen or probably have used macular chamber before. Yes, Danny too have seen it. So 3 down. I just want to know how many have seen, at least have seen. That's why you are learning. All right. So at least you have about 3 people. At least 3 people who have either seen or heard about a maximum. You have the benefit of at least hearing about it, knowing about it. So because this, when we are finished with that, you go to the traditional improved neighbor counting chamber. So it's a counting chamber, as I've said, and it's designed specifically to count sperms. Just as we have the Fuchs Rosenthal counting chamber. Who has heard about Fuchs Rosenthal counting chamber before? Anybody? Fuchs Rosenthal counting chamber. Fuchs F UCHS apostrophe ROS. Who has heard Fuchs Rosenthal? Fuchs FUCHS hyphen Rosenthal ROSENTHAL. Who has heard or seen Fuchs Rosenthal counting chamber before? Nobody? Okay. So you see that we have certain counting chambers are designed for specific jobs. For example, the Fuchs Rosenthal counting chamber is designed specifically to count cells in CSF. Cells in CSF. The appropriate counting chamber to use, the Fuchs Rosenthal counting chamber, is designed. For example, the normal counting chamber we use has a depth of 0.1. I'm sure you know about that. Fuchs Rosenthal counting chamber has a depth of 0.2 and is well designed to be used for CSF. However, in the absence of all these things, we are able to use the improved neighbor counting chamber for all of this, including CSF, including body fluids, including even the semen. So we are able to adapt the improved neighbor counting chamber for all these things. However, I'm saying that the chamber which is designed specifically for semen, or for that matter, sperm count, is the macula counting chamber. I hope that I'm not confusing anybody. Even though we're able to, just as I said, CSF, the appropriate, so if for any examination purposes, they ask you what counting chamber will you use for counting cells in CSF. If the answers don't, if there are answers, the appropriate answer is the Fuchs Rosenthal, please, not the improved counting chamber. However, it doesn't mean that you cannot use this one, the improved neighbor, for the cell count of CSF. So what it means is that it's you are modifying it for CSF. So that's why I'm talking so plenty. So the fact that you are able to use the improved neighbor counting chamber for CSF, sorry, for semen, doesn't make it wrong. But what I'm saying is that it's just an adaptation, but appropriate and recommended and approved special chamber for sperm count is the macula counting chamber. Okay, so it's a specialized counting chamber designed specifically for counting sperms. It gives the concentration of sperms in million per mil. That's what we know. So for sperm, every sperm count should be reported in million per mil. And this one is been designed in such a way that, and as we move along, you see, if you're able to count sperms in 10 squares, whatever number you get, that is your sperm count in million per mil. All right. And as you move along, you get more information on it. All right. My slide is not moving. Good. So this is macula counting chamber. This is how it looks like. This is how it looks like, the macula counting chamber. I'll show you one when we meet physically. But just about this. This is macula counting chamber. But there's supposed to be a cover. This is the space. There's supposed to be a cover glass, which is also rounded. The next picture will show you the cover glass. So this is the counting chamber macula, designed for sperm count. This is one side of it. I hope you've seen it. When you see it, I mean, it looks just about, this is just the exact picture of it, the macula counting chamber. Good. So now let's see how it goes. So upon liquefaction, every semen, before you can do anything about it, it must liquefy. The specimen is mixed by gentle swelling to achieve a homogeneous solution. This one is the same for every procedure. And then an aliquot of well-mixed semen is transferred into a clean test tube. So it means that you mix it and then take a small amount, because if you want to use the whole thing, if you want to use the entire thing for your counting, I mean, as we move along, you see that we are going to immobilize the sperms. The difference between the macro chamber and then the neighbor cavity chamber is that in the neighbor cavity chamber, you are going to use a diluting fluid. And that diluting fluid has the capacity to immobilize the sperms. You know, sperms are moving. Okay, even though that are even just doing that kind of on-the-spot movement, they are still moving. Okay, so if you want to count something which is moving, of course you can't do it. So they must be immobilized. They must be killed to some extent. So in the traditional method, the one that you and I use, you use a diluting fluid, and that diluting fluid must kill the sperm. So it will do that. Here in the macro chamber, there's not going to be any dilution. Okay, yet you are going to count. You are going to use the raw specimen. And so, because you're going to use the raw specimen, you are not going to dilute. The sperms must be physically immobilized. Okay, so if you have somebody produces, let's say 2 mils of semen, and you're going to use everything to go through the process of the macro cavity chamber, it means that you are going to kill all the sperms. Okay, so you just take a little amount of it, and put in the test tube. It is this test tube, the one in the test tube, that we are going to put into a water bath. Put into a water bath of around 50 to 60 degrees. And this temperature, remember we said that even with the with normal sperms, semen, if you expose semen to temperatures above 40 degrees, what will do? They undergo the heat shock phenomenon. Remember that we had a cold shock, and then we had a heat shock. Now, if you expose sperm to above 40 degrees, of course they're going to die. That's why we said that if you leave sperms on the bench, and if let's say they are close to the door, and then you have the sun hitting on it, after 2 hours, if you do this in wet mount, you won't get motility even up to 5%. All the sperms will have died. Okay, so now you are going to expose your specimen to a temperature of around 50 degrees, and that within 5 minutes, all the sperm should be dead. Okay, so that is immobilization. Now, if you don't have a water bath, that can be regulated to the 50 to 60 degrees. All you do, very, very simple, is to what is to test of 100%? You can tell me, to test of 100%. The test of 100%. Okay, so I'm just making you appreciate something. So if you don't have a water bath, which can be regulated to this temperature that we want, and you have the benefit of a macro chamber, and you have to immobilize your sperms, just take any hot water, any boiling water. Of course, you can have a kettle, you boil it, and then you take to test of the boiling water. What it means is that if I have 2 cups, I take 2 cups of it, and then I take 1 of ordinary tap water and add it. Okay, that's around 66. Very good. So if you take a boiling water, okay, if you take 2 parts of it, and 2 parts could be, if you desire to even take 2 cups of it, then the other 1 cup, you add ordinary tap water to it. You are going to get a temperature around 60 degrees. You can try that in your lab. You get around 60 degrees. And that is what you're going to use as your water bath. All right. So now you have a test tube into which you are putting a little amount of the semen sample, and then you put it in there for just 5 minutes. If you put it there for 5 minutes, all the cells will have died. Okay, so that's the first step in doing your macula chamber. Yes, because you are not going to do what do you call it? You are not going to do a dilution. However, the sperms must die. What you do is you expose the sperms to a temperature between 50 to 60 degrees. All right. I hope the point is clear. Good. Now, sperm count, that's on the macula. Sperm count performed from undiluted specimen. Okay. Now we're going to look at how you go to the process in the next slide. The number of sperms counted in any any strop of 10 squares. No, in any 10 squares, that's the problem. Sorry, I will correct it. So in the next, now I'm going to show you the rulings, the lines that are exposed or that are done on the macula. They are 100 squares, 10 horizontal, 10 vertical. So you're going to get 100 squares. If you count sperms in any 10 of them within the 100 space, if you count sperms within any of 10 squares, that is adequate. That number of sperm that you get within that 10 squares is equal to million per million. What it means is that if I counted and I got, let's say, 100 sperms in the 10 squares, then my result is 100 million per mil. Very, very simple. Very, very, very simple. All right. So here you count the sperms in any 10 squares under the grid, and then no additional factors are necessary. The depth of the 10 micrometer is, I mean, everything is set. Okay. And that is very, very simple. So this is the entire whole thing. So let me get you my printer. I hope you are following, ladies and gentlemen. So this is the macula that I showed you. This is the top. Okay. So you just put a drop of, remember, what do you call it? Your sperms, the semen sample must have been immobilized in the water bath. And then just put a drop in this hole here. And then use the cover here, which is a special cover, to cover it. And then you examine under the microscope. Here, the microscope, you know, this one is a big thing. You see how the nature of this one is very, very big. So if you use 40, what do you call it? The high power objective, it will not work. You know that. You know what is called working distance in the microscope. Another microscope. Now, the distance between the what do you call it? The slide, if this is your slide, okay, and then this is your objective. If you focus, the distance between the slide and then the objective is what we call the working distance. This working distance reduces with higher magnification. So you see that if it is 100 times 100, you see that once it's in focus, there's virtually no space between the slide and then the objective. Just a little space, and that little space is what is filled by the oil immersion. Okay. Now with the times 40, the distance is also there is a space there, but that distance is also short. If you use the times 10, then the times 10, the space is a little bit wider. That's why when it comes to maintenance or the proper use of microscope, we advise that if you are removing a slide or taking a slide away from the stage of a microscope, it should always be, it should always have the times 10 in position. The reason is that when the times 10 is in position, the space between the slide and for that matter, the stage and the objective lens is adequate enough for you to be able to move the slide in and out without any danger. However, if you have the times 40 in place, for example, the times 40 in place, the distance between the objective lens and the slide is so small that in trying to move the slide, you can even break your slide. So in proper microscopy usage, you have to always make sure that once you are removing your slide in and out of the stage, you should always have the times 10 in position, because the times 10, and like I said, that the distance between the objective lens and the slide, and for that matter, the stage, is what we call the working distance. The working distance decreases with increasing magnification. So as the magnification is increasing, the distance becomes very, very, very short. So in between the 40 and then a 10, you have times 20. Most of us, we don't use our times 20 objective. Normally, we use the low power, which is times 10, and then the high power. But there is the times 20 there. So if you're doing proper, let's say, semen analysis, and you have the benefit of a macro chamber, you must have the times 20. Times 20 is in between the 10 and then the 40, so that the space, because if you are using the times 10, the sperms are so small that if you use the times 10, the counting becomes a challenge. You can't count. They become too small. If you use the times 42, times 40, the objective lens is giving you a very small working space. And therefore, if you look at the nature of the macro chamber, this is like a huge block, and therefore times 40 cannot even be positioned into place. But like I've said, times 10 is too small. So therefore, times 20 becomes the most appropriate objective lens to use when you're using the macro chamber. I hope my point is clear. So you have the times 20, which will now make it possible for you to locate or position the objective lens in place, because this is very bulky, and therefore if you don't have an objective lens that will have an adequate working space, this thing will not work. I hope my point is clear. So once you have put in your sample, this cover slip, this special cover slip is put in place. Then you put it under the cover, under the, what do you call it, the microscope, and then you use the times 20. You are going to see the cells here, the sperm cells here, and then you are going to see, what do you call it, squares. And I'm saying the squares are 100, 10 this way and 10 that way. And then you are going to take any 10 of them, any 10 of these. So we recommend that you can go diagonal like this. Diagonal from top here to down here, you are going to get 10 diagonally, and it's like a fair representation across board. So here, let's say this one here, two, this two, this three, there's nothing here along that line. Then you count the number of cells. The number of cells that you get, you just add million per mil. So very, very, very simple. So this is on the larger scale, this is how it is. So you put in a drop of your undiluted but heated, and for that matter, immobilized semen sample. You put it here, put your cover slip, which is a special cover glass, and then use times 20. I've explained why you have to use times 20. I'm saying that first and foremost, times 20 is intermediate between the 10 and then the 40, and gives you adequate working space. I'm saying working space is the distance between the cover glass, the slide, and for that matter, the stage and the objective when you focus. And I'm saying that the objective, as the objective is increasing magnification, the working space also becomes shorter. So you see that for times 10, you are going to get enough working space. Times 20, you're still going to get moderate. Times 40, you are going to get a very small working space. Times 100, there's virtually no working space. Okay, right. So because of this one is bulky, you have to use the times 20, which will allow you to be able to focus. If you use the times 10, you can focus, but the sperms too are going to be so small that you may not be able to count them very well. So the most recommended appropriate objective lens to use as far as macro is concerned is the times 20. I've made myself very, very clear. Good. So, and then you are going to get the squares like this. So 10 diagonally, 10 across, 10 down, like so that give you 100. And if you count sperms in any 10 of them, for it to be represented, like I said, you can count diagonally like this. And then you are going to get a certain number of sperms. What number of sperms that you get is if you can, you get 35. It is 35 million per male. As simple as that. Very, very, very simple. Very, very, very simple. So the total number of sperms counted within the 10 squares in the macro chamber is equal to the sperm concentration. And for that matter, the sperm count in million per male. No further calculation is required. So for example, if 35 sperms are counted in 10 squares under the chamber, then the sperm count is 35 million per male. Okay. All right. So that is the macro chamber. Any question? Any question? Okay, so you move on. So then you move to the almighty improved neighbor counting chamber. Like we said, now everybody, it makes it look as if to do sperm count, you need improved or the neighbor counting chamber. But you see that this is rather an adaptation. The properly designed special counting chamber for sperm count is the macro counting chamber. Okay. If you are lucky to have some, as some of you have already, that's great. You don't do any work on it. Just a drop onto the chamber, apply the cover, use the times 20, and then get it in focus. We're going to get a squares. You count the number of sperms in there, and that's all. No calculation, nothing. You don't do any dilution. And because you don't do the dilution and the sperms will have to be mobilized, you expose the specimen to a temperature of between 50 to 60 degrees. And we said that you don't expose the entire specimen because you may be using the specimen for something else. Okay, so just take a little amount, just 150 microliters. Because after all, what you are going to use as a drop for this is just about 10 microliters. Okay, so just small amount is what you are going to immobilize. And I've shown you how to even immobilize if you don't have a water bath. That you heat water to test of it two parts, any 2 parts. If you can make, you can take if a syringe, take 20 ml of the hot water and take 10 ml of the other tap water, you get 30 ml. This is likely to give you a temperature around 60 degrees. And I suppose put your test tube, in which you have your small amount of your semen, which you have mixed very well already. When it has already liquefied, you have mixed it, and then take a small amount into your test tube, put in the water bath or into this Aprotec kind of water bath, which we have just described. For within 5 minutes, you are done. And then, yes, total number of sperms is any 10 squares. And over there, you have 100 squares. Okay, you have 100 squares. You have 100 squares. Any 10 of them. Any 10, but it should be representative. If you go this way, it's like I don't know how to put it, but this is the whole broad. So if you want to take 10, I think 10 should be taken in a manner that it can be a true representation of what is happening here. That's why I'm saying that I recommend that you go diagonally. Diagonally is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that will be a true representation. If you can go, if you want to take a 10 here, that's okay. If you want to take 10 here, that's okay. But any 10 squares will give you your sperm count per male, million per male. Is that okay? Good. So now we're going through our normal, the one you and I know about. All that I wanted you to know is that if, for example, any particular examination, and they are just as I talked about the Fuchs Center, if for examination purpose they ask you what chamber will you use for sperm count, please, the answer is not improved neighbor county chamber. The answer will be the macula county chamber. However, in the absence of macula, we are able to use this one for the test. Sperm count in most laboratories are traditionally performed using the improved counting chamber. And as for the improved counting chamber, I'm sure everybody has seen one and you are using it. In this procedure, dilution of well-mixed liquefied semen sample is required. A sperm mobilizing diluent is also required. I hope you get it. So here, you are going to use a diluting fluid, and that diluting fluid must be one which is able to immobilize, for that matter, kill the sperms. Okay, and we are also going to see the other procedures that go along with it. So sperm count using the improved neighbor counting chamber. The principle of sperm counts using the improved neighbor counting chamber, and for that matter, hemocytometer, is the same as for total WBC counts in whole blood, or cell counts in CSF, or other body fluids. So unfortunately these days, because of the auto analyzers for hematology, I'm sure nobody does manual WBC count. Even in school, I'm not sure they teach you how to do manual WBC count. And therefore, people complete school, they come to microbiology, where cells from body fluids, including CSFs, are counted using the neighbor counting chamber, and everybody has a difficulty, a challenge, because okay, they are teaching. Okay, thank you for correcting me. Thank you for correcting me. So you learn how to properly use the improved counting chamber and all the technicalities with it in hematology. All right. So what you're saying is that the principle of the sperm counts for semen is the same thing as you will have done for WBC count in whole blood. Okay, so they say everything is the same, except that the diluting fluid, of course, will have to change. Okay, right. And of course, sperm count in semen is reported in million per mil, whether you're using the macula or you're using any other chamber. Sperm count is reported in million per mil. Okay. Now, we said that the principle for the sperm count is the same thing as the WBC count. However, for example, in total WBC, the whole blood is reported as something times 10 to the power 9 per liter. I'm sure all of us know this one, because we said that everything is like WBC. So if you don't make the differentiations, I think you could have challenge with some people. So yes, everything is the same, but reporting for the WBC is reported as something times 10 to the power 9 per liter. Okay, that's the standard reporting for WBC. When it comes to WBC2, it is reported in cells per millimeter cube, something per millimeter cube, either per millimeter cube or per microliter. Remember, millimeter cube is the same thing as microliter. Remember when we are trying to check for the possible depth of the suspension under if you do a wet mount, if you apply 22 by 22, and then you take a 10 microliter, drop of 10 microliters, you're able to calculate. Remember, we said that the microliter have to convert it to millimeter cube, okay, so that you can do your calculation. So all that you're saying here is that you can write your report when it comes to cell count in CSF. You can report in per millimeter cube or per microliter because they are the same thing. All right. However, for the semen or sperms, you are going to report in million per mil. All right. So this is the differentiation that I wanted to bring to your attention. So if you are going to do the sperm count using the improved neighbor country chamber, of course, you need your sample. You need your hemocytometer, which is the improved neighbor country chamber, and a cover glass. All right. Many people, all of us, appear to be using the normal cover glass 22 by 22 for the country chamber. Now, yes, we can use it, but I'm sure you know that when you get any new hemocytometer or any new improved country chamber, I'm sure that you know that it comes along with a special cover slip. Okay, that cover slip is thicker than the normal cover slip that we are using. Okay, so take note on that. And why do you need a thicker cover slip and not the normal cover slip, even though you're able to use the normal cover slip for it? It is not appropriate. So what it is that if you're doing something and you know that, oh, you should have used this one, but if you don't have this one, you can use this one. You must know the reason why you are using the other one, okay? So that if somebody should question you, you know how to explain yourself scientifically. So the cover slip for the hemocytometer, and for that matter, the country chamber, is thicker than the ordinary cover slip. However, in the absence of it, you're able to use the normal cover slip. As we move along, I'll try to explain why you need that. You also need a tally counter. Now, tally counter, I'm sure all of us have seen the tally counters. And I think I have a picture of that I will show you. And then you also need the semen directing fluid. We'll talk about how to prepare it. Of course, you're going to need a disposable pasta or transfer pipette. You need a test tube 12 by 75, that's a small test tube, okay? Because we are going to do your dilutions. And the dilutions must be done in a test tube, okay? Not in a very light test tube. Because normally, for convenience, we use drops to do the dilutions. And so if you have a very large tube, I'm sure it may not be very convenient. So we use a small test tube of dimension 12 by 75 millimeters. And then micro pipette, which is optional. Okay. Normally, if you want to charge your chamber, if you use a micro pipette, then you can deliver exactly a certain amount to charge your chamber. Again, if you have a micro pipette, instead of using drops, if you want to use a certain volumes to do your dilutions, then that one. So, but in the absence of the micro pipette, the transfer pipette can still be used for whatever procedure that you want to do. So you see that in doing your counting, counting by the neighbor county chamber, you need a lot of things, as opposed to the macla. Macla, all you need is your sample and then your chamber, period. You don't need anything again. All right, so let's move on. So I'm sure you know a lot about the improved county chamber. I just want to bring your attention to the fact that you have what we call a standard form and then a V-load form. A lot of people probably haven't taken note of this. Now, the standard form has a straight edge here. And then the V-load form has some ditch here. and takes the form of a V. That's why we call it the V load. Now, if you put the cover slip on it, and then you are charging the chamber, it means that you must incline your pipette, because you put your cover slip, put the cover slip on it here, and then you are going to charge the chamber at the edge here, and that edge, it means that you must be careful how to do that. Okay, so you incline your what do you call it, your transfer pipette or capillary to whatever you are using to charge it at this edge, and then try to get it charged. Over here, you are still going to apply your cover slip, all right, but there is a convenience place for you here. So you just drop your sample here, and then also goes in. So this is just for convenience sake. I hope that you are getting me. So the new versions that are coming in are all the V-load type. The V-load is just nothing, it's the same thing, except that they are making convenient for charging, so that you don't have to be struggling to put the capillary tube or the pipette in a manner that sometimes before you could say that the specimen has rather been released onto the onto the cover slip, and nothing is moving down. But with the V-load, it's just for convenience sake. I hope that point is clear. Right. So you have these types of, and you know that this cover slip is completely different from the normal cover slip. This one is thicker and it's longer. Okay. Thick, let me explain here. Thick because now look at this. It is the shape of an H, okay? It is like an H. It is like an H. And whatever is here is a replica of what is here. Okay. So the idea is that it was being used in such a way that if you have a particular sample, not necessarily the semen, whatever you're going to do accounting for, it is supposed to be duplicated. So you charge here, if it's sample 1, you charge here, and then you charge here. So that you're going to do the count here, you're going to do the count here. When you finish, you find the average. But these days, nobody who wants to, I don't know, nobody wants to do that kind of double work. So instead of using the same sample here and counting here and here and find the average, you rather use one sample here and then use another sample. So if this sample 1, this should be another sample 2. But I'm saying that the intent of this was to duplicate, so that the same sample should be read or should be recorded 2 times, so that when you finish, you find the average and count and find the average, so that it becomes more reliable and accurate. I hope that point is clear. All right, so that is it. Now let me come back to a cover slip. This cover slip here is supposed to be laid on top here, and you see that the block here and the block here are higher than the platform here. So this one and this one here are on the same level, okay? But this one here is lower than this side. So if I put the cover slip on it, then it is going to leave me a space down here. And that is the space which we call the depth of the chamber. And this is the value, 0.1. So 0.1000 this is the depth of the chamber. It means that if I put a cover slip on it, this block here and this block here, I put a cover slip on it. And because these levels are higher than this level, if I put the cover slip on it, it will leave me a space below. And that space below is what we call the depth of the chamber. And it's supposed to be 0.1 millimeters. I hope that one is clear. Good. Right. So the improved neighbor county chamber may come in the standard form or the inclined, because you have to incline to deliver the specimen, or the V-shaped or the V-load type. With the V-shape, the cutouts of the chamber allowing for easy loading. I'm sure this is what I've explained already. The top and bottom counting areas can be loaded independently. They can be loaded independently. What it means is that if you have two specimens, you can load one here and can load one here. But what I'm saying, the original intent is that it should be the same specimen, which should be loaded here, loaded here. When you finish counting here, you count here, and then find the average. All right. Good. So on the, once you put, I think I didn't explain this one enough. When you put on the cover slip, the space here is supposed to be the 0.1. Okay. When you put a specimen here, which we call loading, when you load the specimen here, the load here may try to push or pull this cover slip up a little bit, because you know they say water finds its own level. So if you have a certain suspension and you put the cover slip here, and then you are pushing specimen here, if this cover slip is not thick enough, what it will do is that it will allow itself to pull up. So this one is going to pull pull this one up, and therefore the specimen which is going to go here is going to be the volume is going to be more than what you have to calculate. Because take note, when we finish, we are going to calculate the volume under the chamber. The volume under the chamber is going to be this area, okay? The area here, multiplied by the depth, because you are going to put a cover slip here. The area multiplied by the depth will give you a certain volume. And that is the volume that you are going to use in your counting. Okay, so, and that volume will be specific, okay? Because the area here is the area here is like, how do I put it? It's defined. I mean, there's nothing you can do about it. And then the depth here too is also defined. But if you do anything that will increase the depth here, then it's also going to increase the volume. Okay, so the concept of giving a special cover slip which is thicker is to make sure that it is thick. Once it is laid, the volume that goes here will not have it, will not have the capacity to move it up. If you put an ordinary cover slip, they are lighter, and therefore the possibility of the fluid here pulling it up becomes higher. And once it pulls it up higher, what is happening? The volume is going to increase. And the volume, when the volume increases, how can you compensate for that volume? You don't know what volume. So it means that all your calculations will go wrong. All right. So coming back, now you know that you have a depth of 0.1 millimeters. So if you have this one as your cover slip or cover glass, and then this size here will be the blocks, and then this is going to be the platform on which the counting is going to be done, and this space here between the cover slip and the platform is the 0.1. Okay, and on the platform you have these lines ruled over there. These lines have been ruled on the platform. Let me go back. So on this, if you look here, I'm sure all of you have seen cover slips before. I've used some. You see, if you look here, you see that there are some, it gives like an indication of a cross. The lines have been ruled vertically and horizontally. And therefore, here's this where you have your rulings called the grade. The rulings are here and here. Okay, right. And this is the nature of the rulings. So it goes like this. You have a central area. Okay, you have a central area here. See that the central area here rulings are different from the corners here. So if you have a big cross here like this, I mean, two big lines here, and then under two crossing over, you are going to get these ones as your corners. And remember, everything here is a square. So if this one becomes your center, then this one becomes your corners. So you call this the four corner squares. It's a square. It's a square, but they are the corners as far as this central portion is concerned. So we call it the four corner squares. Now you are going to count cells within these spaces, but the cells too are small things. The cells are small. So if you leave this entire space out and you have cells here, you see that when you are going to count, you are likely to overlook some, assuming that this square here was without further lines. Then it means that if you have cells dropped here and you are counting, you have no guide, and therefore you could miss some. Okay, so the essence of the lines here is to redivide the square here into smaller squares so that you can concentrate on each, so that as you see this one, you can concentrate on the square. And if there are cells here, you can just concentrate on them and then count them and then move, and come down, so that it gives you that kind of flexibility to be able to count the cells per each of the small squares. So there's division here is just to allow for convenient, what do you call it, counting, so that you can, even when you are counting and you reach here, you can stop. And then knowing that, oh, I counted, and when I was counting, I'm going here, coming here, and going here. So if I've counted and reached here, and somebody disrupted me, I can come back and continue from here, and then go and count. But if there's no lines here, then it means that if you start counting, there's any least disruption, you come back and you don't know which cell you counted. Right. So that's the first thing. So the divisions here is to allow for easy counting. Good. Now let's look at some calculations. This whole here is a square, and the dimension here is 1 millimeter. So if it's 1 millimeter, then the entire stretch here is going to be 3 millimeters. Okay, the entire stretch here is going to be 3 millimeters. And then the entire stretch here is also, because it's a square, the entire stretch here is also going to be 3 millimeters. Therefore, the entire area here have a square of 9 millimeter square, because this is going to be 3, this is going to be 3. So the area is length as breadth, and they are the same sizes. So it's going to be 9 millimeter square. So this is what we have here. So the entire large square here has an area of 9 millimeter square. All right. And each corner square here will have an area of 1 millimeter square, because this is 1, this is also 1. So the area here is going to be 1 millimeter square. Okay. I hope that one is clear. The smaller squares here, you can ignore them, because they are just to guide you to do your counting. You can, however, if you want to actually do the mathematics of it, what it means here is that if this is 1 millimeter, then what will be the size? Yes, you can tell me. I say it is not important, but assuming you want to do some mathematics, what will be the size here? You can tell me. What will be the size of one small square in the large corner square? Some people are dropping off. The number has reduced to 18 now. All right, so what will be the square here? What will be the size here? One small square at the corner square. Yeah, somebody should tell me. No. Come again. Julius, he said 1 divided by 4, but 1 divided by 4, I want an answer. Then what do you mean by 1 divided by 4? What is 1 divided by 4? You are correct, but what is 1 divided by 4? Yes, come again. Correct. So 0.25. So this size here is 0.25. And therefore you can calculate the area here. One smaller square of the small square areas. You can calculate it. That's 0.25. Multiply by another 0.25. Okay, so you can do that. Now, if you come here, this is very, very interesting. If you come here, so let's go back here. So here, divided into 16 squares. 4 here, 4 here. Let's give the 16 squares. You don't need the calculation for anything. The calculation you need is this larger area, which is 1 millimeter square. You're going to work on that. If you come here, this space has been divided into 25 squares. Okay. No, this is wrong here. This is wrong here. I'll show you. Let me see if I have a better picture. But this, of course, this is a picture that I got from the internet. But this is wrong. Rather, the internal squares here, the central square here, is first divided into 25. Here, they are still maintaining the 4. Here, you see that there's 4 here, isn't it? 4 here, 4 here, and 4 here. They are maintaining the 4 here, 1, 2, 3, 4 here. Rather, it is first divided into 25. Let me see if I can get a better lesson. And I need to explain this one to you very well. Very good. This one is better. Let's look at this one. Please take note of this one and take note very well, because you may not, you may have seen it, but may not be able to know what it is. So look here. I'm saying that the first diagram is wrong. And but here, look here very, very well. The center here. The center is divided into 25. Look here, you are going to get 5 here. So this is 1, 2, 3, 4, 5. So this has been divided into 5 here, and of course 5 here. So it means that this central area has been divided into 25. If you go back, the one that I said that I haven't even taken this one. You see that it's divided into 4. 1, 2, 3, 4. This is wrong. This is wrong. So coming here, this is the right one. It's divided into 25. So it means that this side here is 25. And this side is also, so this side is 5, this side is 5. So this small area is 25. Now, this small area has been subdivided into 16. Okay, so if it has been subdivided into 16, what will be the, let me take it one by one. So it means, what is the size here, as you did for the first one? And you got to know that this size here, one of the large corner squares, the size here is going to be 0.25. What will be the size here? This size here. Yes, you can tell me. For the central square, which has been divided into 25. What will be the size here? You can tell me.
0.2, Grandpa.
Yes, people are still dropping off. Are you tired or just network? So no. Yes, Julius is correct. Julius is correct. So the size here is 0.2. This one. The size here is 0.2 because instead of the 16, you are now having 25. It means that, and it's still the 1 millimeter. So the 1 millimeter must be divided by 5. So 1 divided by 5 will give you 0.2. So it means that the small size, the small, what do you call it? The small square here has a size of 0.2 by another 0.2. Now, this small size has been subdivided into another 16 squares. Okay, this side has been subdivided into 16 squares. So what is the size of the smallest square? The size, who can tell me? Yes. When you're able to tell me that, it means that you're actually following it. Now this side, the central area has been divided into 25. And you know that it means that each small square here has a size of 0.2. And I'm saying that that small size has been subdivided into 16. So what would be the size of the smallest square in the central area? Yes. No. This one is wrong. Let's come again.
Grandpa, 0.0125.
Yes, I want everybody. Why is it that only Julius is trying? Everybody, you should try it.
Grandpa,
the size of the smallest square in the
Grandpa,
central area will be what? The size will be what?
Grandpa.
People are still dropping. Now you have 16. Minus
Grandpa.
Myself and then the director. Okay. Yes, you can tell me.
Grandpa.
Please try it. I know you can do it.
A 0 point.
Julius, come again. You get it. Yes. Please come in. Oh. This one there. See, you have to know this because students come to your facilities and you must be able to explain these things to them so that they can appreciate it well. Okay, the lines are not drawn for nothing. Okay. Last chance. Who can do it for me? Okay. So let's work it together. This is the central area. It's still part of the larger square. So therefore, the size here is 1 millimeter. And I'm saying that the first ruling is that it has been divided into 25. So once it has been divided into 25, it means that this side has been divided into 5. This side has been divided into 5 to give you the first 25. So it means that if you want the size of 1, it must be the 1 divided by the 5. Because now you want to know the size of one of this. So it is 1 divided by 5. Here it was 1 divided by 4. And then because it has been divided into 16. So you divide it here by 4 and you get it 0.25. Okay. Now, if you come here, it has been divided into 25, and therefore each side are divided into 5. And therefore, the size here is 1 divided by 5. That should give you 0.2 here. Now, this 0.2 has been subdivided into 16. So for 16, it means that this side has been divided into 4, this side divided into 4. So it is 0.2 divided by 4. That's going to give you 0.025. Okay, that's going to be so it means that the smallest size of the square in the center is one side is 0.025. So what will be the area of the smallest size in the center? Yes, come. This one everybody should get it correct. Now we say that so the size of the smallest square in the center is 0.025. I hope you understand it. It's going to be the 0.2 divided by 4. Okay, 0.2 divided by 4 is going to be 0.025. So what is the area of the smallest square? Yes, this one, yes. I thought somebody, Vera, no, this one is wrong. So the area of the smallest square The area of the smallest square, please. Please, don't disappoint me. The area of the smallest square. Yes. 0.000625. Who is this? Oti, fantastic. Great. And now let's go back. You see, let's go back. Now, no. I wanted to check on something, but I think there's something wrong here. Where is this 0.5 coming from? Oh. There is, I wanted, no, I think there's something wrong. I think I made a mistake somewhere. That the this thing, the size here is rather not 0.025. I think I made that mistake and nobody corrected me. So the size here, the central square area, the size here is what? 0.2. That one we agree. Is that not it? So the 0.2, if you divide by 4, what do you get? I made a mistake and nobody corrected me. Please, let's get this one once and for all. I myself made a mistake. I wanted to be corrected. No, I'll tell you why I saw that I've made a mistake. You see, this is the entire central area here is 1 millimeter. This one, no mistake. It has been first divided into 25. It means that each side must first be divided by 5 to give you a size. And if you divide 1 by 5, you get what? If you divide 1 by 5, you get what? There's 0.2. Are you following that? Let me see if I have my calculator here. So 1 divided by the first 5, that will give you 0.2. So that will give you the first 0.2. And now I'm saying that this 0.2 has been subdivided into 16. So it means that each side there has also been divided by what? By 4. So it means you have the 0.2 now divided by 4. And that should give you 0.05. This is the mistake that I did. I said 0.025 and nobody corrected me. So that is going to give, it means that the smallest size here is 0.05. Please calculate if you get that. If somebody is getting different thing, let's know, because, and this is what it is. 0. The 0. No, even this one is wrong. Or this is 0.05. Okay. So I want you to get this things once and for all. So the smallest size here is 0.05. What is the smallest area? What would be the smallest area? The size is 0.05. What would be the smallest area? Okay, so Julius, you are now correct. So what will be the area of the smallest square in the center? 0.0025. Very good. So So now going back to that's where I saw that I was wrong. So you see that on the chamber, there is this value here. Sorry, let me be sure. You see on the chamber, you have 0.0025 here, square here. Do you see this? You see that on the chamber, you have 0.1 here, and this 0.100 is the depth of the chamber. This 0.0025 millimeter square here is the area of the smallest square on the chamber. And that's where I was trying to. So when I came here, I saw 0.0025. I knew that I had made a mistake somewhere because this one cannot be wrong. This one is 0.0025. And this is the area of the smallest square under the chamber. And the area of the smallest square under the chamber can only be gotten at the central area. Okay, so you should take note that at the central area here, you are going to get the smallest square area there. And the smallest square area is 0.0025, which has been written on the block of the chamber. I hope that point is clear now. Hello? I hope it's clear now. Good. So this thing tries to explain everything there. All right. So let me go back again. So if I'm doing the calculations and I'm concentrating my count at these corners, then the volume I'll be dealing with can be calculated because the area here is 1 millimeter square. The area here is 1 millimeter square. Area here is 1 millimeter square, 1 millimeter square. Now, this, remember, is on the platform here, and it has a depth of 0.1. This 0.1 will not change. That's why I said that if you put ordinary cover thread there, the tendency is that if you load here, it's likely to push this cover thread up and try to increase the volume of the specimen going down there. But if this one is thick, then once it is put in place, the 0.1 becomes fixed. Once it becomes fixed, then the area here can be multiplied by the depth of the chamber and you can calculate your volume. So the volume here is the 1 millimeter square multiplied by what? You can tell me. The 1 millimeter square, I want to get the volume here. What will be the volume here? It will be what? Yeah, somebody to help me. Somebody, please help me. The volume here of 1 corner square will be what? The volume of 1 corner square, knowing that the area of 1 corner square is 1 millimeter square, and the depth is also constant, 0.1 millimeter square. Sorry, 0.1 millimeters. What will be the volume in 1 corner square? Please help me. Let's finish fast. The volume for 1 corner square will be what? Please help me. Who is coming? The volume of 1 corner square will be what? Oh, okay. So, okay, let me see the answer coming up. 0.1 millimeter cube. Fantastic, OT. Good. That's great of you. So, you know that volume is area times height or area times depth. The area here of 1 corner square is known. The area is known. It's 1 millimeter square. And then the height is also known, 0.1. So the volume here is going to be the area times the 0.1. But here, rather, the unit becomes millimeter cube because you have millimeter square multiplied by 0.1 millimeters. Therefore, the unit is going to be 0.1 millimeter cube. So if I count cells here, and I count cells here, I count cells here, I count cells here, what will be the total volume that I will have occupied? Yes, you can tell me. the four corner squares. If I count cells in the four corner squares, what will be the total volume that will have been used up? Yes, somebody come in. Help me, Oti, please. Don't disappoint. The total volume to be occupied or to be counted for the four corner squares will be what? The total volume. Fantastic. 0.4, and I'll give it to you. I'll give you extra marks in your exams, okay? Good. So that will give you 0.4 because the area here is 1 millimeter square, and that is fixed. We know that. Good. Okay, thank you. The area is fixed. It's 1 millimeter. The depth is also fixed. So it will give you a fixed volume of 0.1. But I'm going to count here, count here, count here, and count here. So my total volume will be the 0.1 multiplied by 4, and that will give me 0.4 millimeter cube. And this is what you are going to use in your sperm count calculations. So if you don't know this, if you don't understand these fundamentals, it becomes difficult. It becomes difficult. All right. So now that you have understood it, I think we can move forward. So this is what I've explained already. All right. So some of the things that we also need is a tally counter. This tally counter is very common. A lot of people, but sometimes people don't. They use their eyes and their mind to be calculating, and if there's any small interruption, you can get it off. But if you have this tally counter, I mean, you are counting the cells. You are just so you just look at it and then you are going. So if you have a tally counter, fine. This one is not difficult to get on the market. But people are using their eyes and their mind to just do the calculations. So this is a tally counter, hand tally counter. And then the diluting fluid. The diluting fluid is also very, very, very easy to prepare. You don't need, if I see some lab scientists going to buy saline, I ask myself, what kind of work you want to do? If saline, you have to go and buy prepared saline from the market. It's not good. You have to be able to prepare your own saline. Similarly, diluting fluid for sperm count, you don't have to go and buy. You can do it yourself. Very, very simple. It's 5% of sodium bicarbonate. And sodium bicarbonate too, if you even get one container, you can use it for about 5 years. I mean, it is also very commonly available from any of the suppliers. Sodium bicarbonate, okay, or sodium hydrogen carbonate, right? So it's 5%. So if it's 5%, it means 5 grams in 100 mils. As simple as that. 5 grams in 100 mils. If you want to prepare lower, if let's say you want to prepare 50 mils, then it means that you divide the 100 by 2, you get 50. And you also divide the 5 by 2, you get 2.5. And then the formalin, you are going to just add a little amount of formalin, raw formalin. For each 100 mils, you add 1 ml of formalin. Okay, so that 1 ml of formalin, under normal circumstance, you should have taken 1 ml from the distilled water and then add it so that it gives you the 100, but it doesn't change anything. How that one is clear. So the entire volume should have 100 mils, which means that because you are going to add 1 ml of the formalin, your 100 mils should be 99 mils, so that the volume of formalin will add up to become 100. That is if you want to very, very, very critical. As you said about the Kruger's critical classification, where any small deviation from the normal morphology, it is taken as abnormal. So what I'm saying here is that if you have prepared your diluting fluid, the 1 ml, you don't need to be so critical. You can just take your 100 mils of water and still take your 1 ml of the formalin, and it works for you. Okay, so 5% sodium bicarbonate, 5 grams in 100 mils, and then add a little amount of formalin. The little amount of formalin is just to preserve the cells, the sperm cells, that's all. But the bicarbonate will immobilize the sperms. And then also it has the tendency, you know, semen is viscous. And the bicarbonate is just try to digest it, so it become more fluid. Okay, Right. So the solution may be changed with crystal violet. Okay, the solution can be changed with crystal violet, just as you have with it. You know the text fluid. Who knows about text fluid and what is it used for? Text fluid. The text fluid. What is the text fluid and what is it used for? Yes, somebody should help me. Text fluid. Text TURK apostrophe X. Text fluid. What is it? And what is it used for? Yes. Text fluid, TURK apostrophe X. Text fluid. What is it and what is it used for? Oh, Ebis, I remember you said that now they are teaching the WBC, manual WBC counting, WBC counting in schools. You said it when I said that we are having challenge with people come to microbiology. They have challenge with counting cells using the neighbor counting chamber because these days people are not using the manual counting chamber, manual WBC counting. And you said that now they are doing it. So if they are doing it and you don't know text fluid, so text fluid is the WBC counting, so WBC diluting fluid. It's just 2 to 3% acetic acid. Okay, 2%, 2 to 3% acetic acid. That is the WBC diluting fluid. And in that fluid, you tinge it with, that's why, this is where I'm coming from. You tinge it with crystal violet. Or if you're in hematology, GIMSA, you tinge it with GIMSA. The idea is that when you say tinging, it's like a man when they are washing white clothing, will be afraid blue. So the water, the last water, they add just a little blue coloring this thing. So tinging is just adding something small just to change the face of it. So you are not adding the blue, you are tinging it. So the crystal violet tinging is just dyeing the color just a little bit, not too much of it. So the WBC diluting fluid, which is 2% acetic, is called text fluid. Take note so that when students come to your facility and they are going to write external exams, these are the things they tell. They won't say WBC diluting fluid. No examiner will say that. They'll mention text fluid, and text fluid is the WBC diluting fluid. It's just 2 to 3% acetic acid, tinged with either crystal violet or GIMSA. And the idea is that crystal violet or GIMSA is just to stain the nucleus. It doesn't, because it's just give the nucleus just a little bit a tinge of a color so that it can differentiate from, let's say, other debris. All right, so the same thing is happening here. The actual solution is 5% sodium bicarbonate with the formalin. I've told you what the formalin will do. And then it's changed with crystal violet. What it means is that once you have finished your dilution, you can just add a little bit of crystal violet to it. And that gives you your semen or your sperm or semen diluting fluid. Don't go and buy this anywhere. Okay, right. And you store it, and the solution is stable indefinitely. It means, what it means is that you can even prepare 1 liter. Okay, the only thing is that when you are going to use, you have to filter because sometimes it can collect some debris and can influence your counting. So as you're going to use it, you try to what do you call it? You try to filter it. So 5% sodium bicarbonate. If you want smaller volume, you can do your calculation. If you want larger volume too, for example, if you want 500 ml, you multiply the 100 here by 5. You are going to get 500 ml, and you multiply your 5 grams also by 5. You are going to get 25 grams, and you multiply your 1 here also by 5. So you are going to get 5 ml of formalin, 25 grams of sodium bicarbonate, and 500 ml of the water. And as for the crystal changing, just adding just a little bit of it to give it a certain small color. That's all. So that is your diluting fluid. All right. I think people are getting tired. They may want to. So let's take this important. In the absence of the traditional diluting fluid, which is the sodium bicarbonate formalin reagent, clean tap water may be used to dilute the semen. Okay, so that if all of a sudden you realize that your diluting fluid is finished, and meanwhile you have a case to work on, you can use tap water. Okay, because remember that if you put tap water to, as we move along, we're going to talk about the hypoosmotic effect. No, water will move into the sperms and then will kill it. All right, so in emergencies, you can use clean water to do that, but don't use clean water as your regular diluting fluid. Okay, your regular diluting fluid is 5% sodium bicarbonate with formalin, tinged with the crystal violet, and then that is all. In case where water may have to be used as the diluting fluid, the semen sample should first be placed in the heat block or water bath assisted. Remember that we said that if you allow the water to be clean, it may take a long time. Okay, so you can fast track that one by immobilizing it as we did with the macula chamber. And now you can add your water as your diluting fluid. Okay, we have a lot to work on, and I don't know whether you are getting tired. If you are getting tired, we can close and continue from tomorrow. If you think you want to continue you can continue, at least finish with the counting. Let's see by hands those who think we have to continue. If you want us to continue, let's show, or you are tired. I'm getting the impression that a lot of you are tired. Okay. So in order not to force ourselves so much, let us end here. We'll try and finish it tomorrow. So it means that tomorrow it will be a marathon. Okay. Tomorrow we will do a marathon. So today we are trying to end here, and then tomorrow, God willing, we'll finish. So get ready. Tomorrow, come early. 6 o'clock. We start at 6. So only I wanted to make sure that every step of the way you are following. That's why I take my time and go over some of these things over and over again. Otherwise, we could just go very fast and finish. But we don't want a situation where you finish this course and people will still have a challenge. After this course, you should be a master on your own and be able to even to teach people to do the right thing. Okay. All right. So let's end here. Tomorrow, God willing, you'll continue. And God willing, I'll try and finish tomorrow. Good night.